Okay, for this chapter, let's talk some about compounds. So, first, if I told you to mix together 1 part green poisonous gas and 1 part explosive metal, and to add that to your hamburger to make it tastier, you'd probably not think that was a very good plan. I know if I read that description, I'd be like, that sounds like a recipe for something kind of dangerous and probably not good for me. However, in chemistry, compounds work a lot like this. We mix together 2 or more elements to form a compound. That compound has properties vastly different than what it was before. So in the case of the above, chlorine gas is poisonous, and sodium metal readily reacts in water to catch fire. But when they're combined together, they form a compound that forms table salt, which I think overall is pretty nice on my hamburger. So in this chapter, we're going to explore the ways in which compounds form to have vastly different properties compared to their starting components. So let's start with going from elements to molecules. So far in all the previous chapters, we've only talked about elements on their own. If everything in the world could only be made of one of approximately 118 different elements, then there would not be many substances in the world, especially because about 30 of those elements don't exist naturally, maybe a few more than that actually, but a number at the bottom we have existed for things like microseconds or picoseconds that we know they technically exist, but you can't do a whole lot with some of them. However, elements can be combined to form molecules, which gives significantly more options for materials in the world, thankfully. Anytime 2 or more different elements are combined, we call that material a compound. Anytime 2 elements are combined, that material is called a molecule. What this means is that all compounds are molecules, but not all molecules are compounds. Most obvious example would be if you have 2 oxygen atoms and you combine them together, they form O2. O2 is a molecule because there's more than 1 atom in it, but it is not a compound because there's not 2 or more types of elements. On the other hand, if we have CO2, that's still a molecule because there are 2 or more elements, and it's also a compound because there are at least 2 different elements. There's carbon and oxygen. All of the diverse matter in the universe is made out of some combination of the elements on the periodic table. So we get a lot of different elements because you can combine them in vastly different amounts. It's not just 2 atoms. It can be 3, 4, 5, 6. Depending on your compounds, you start working with biological molecules in your body. They might be made of hundreds of atoms, some of those atoms being the same element, but you quickly get a vast variety of things, whereas if you only had the 118 elements, you wouldn't have that much stuff. So let's take water. It's a good example to help show how to think about compounds from their elements. So all compounds are made out of elements. Those properties cannot be predicted by just combining the properties of the different elements. So let's take water. Water is a molecule made out of 2 atoms of hydrogen and 1 atom of oxygen. Water is significantly different when compared to those elements, though. Hydrogen and oxygen are both gases at room temperature. Hydrogen's explosive. Oxygen's necessary to make things combust. Water, on the other hand, I spray on a fire to extinguish it. In most cases, there are a few types of fires that you don't put water on, but in general, if I'm a firefighter, water's great. I would not want to spray a bunch of oxygen on my fire. That'd be bad. I definitely don't want to spray a bunch of hydrogen on my fire. It explodes. That's what makes the Hindenburg. So for this reason, we can't just say, oh, water is like oxygen and hydrogen. They both are either explosive or allow combustion, so of course water would too. That's not true. So you cannot make a prediction for a molecule by looking at the atoms it's made up of and say, oh, this new molecule must be made of those components. Throughout this class, and if you stick with us in chemistry for a very long way, we'll talk about different ways to help make predictions about how compounds function. There are some ideas we have of how to make some predictions. There are things like software that can help predict how really large molecules function, but it's not simply just taking the properties of those atoms and saying, oh, when we combine them together, they must behave similarly. So we've got a few rules we want to talk about here that help us talk about compounds. So first, we have the law of definite proportions. What this one says is that when we make a compound, there always have to be set ratios of the atoms. So for example, with water, you always have to have 2 hydrogen atoms to every 1 oxygen atom. Now, the number comes from the subscripts written by the compound. So in this case, there's a small 2 by the hydrogen, which means there are 2 hydrogen atoms. There's a which means you have that. If I don't have a number written, though, there's an understood 1. So in this compound, there's no number written next to the oxygen, so we assume there's 1 oxygen atom in every molecule. Now, If you wanted a molecule to instead have one hydrogen atom per one oxygen atom, it would now be a new compound and no longer be water. So to be water, you must be exactly 2 hydrogens to 1 oxygen. It doesn't matter where your water comes from. It could be, as long as it's liquid water like we're talking about here, H2O. So it could be from the Mediterranean Ocean. It could be from a lake. It could be from a stream outside. It could be from the rain. Note that some of those sources might have other things dissolved in them that make them different, but the water itself is all going to be H2O. Even if maybe it's salt water, it has some sodium chloride and some other compounds in it, but the water itself is still H2O. It would not suddenly have 3 hydrogens and 1 oxygen. That's now a new compound. We also need a way to represent these, so we use chemical formulas. So we're going to use this to designate what it is we are working with. So how do I talk about different substances? I'm going to use chemical formulas. So for example, carbon monoxide is represented as CO. That's a compound with 1 carbon and 1 oxygen atom. Whereas carbon dioxide is instead represented as CO2. That has 1 carbon atom and 2 oxygen atoms. We're going to divide these formulas up into a few different types. There'll be 3 we're going to talk about in this class: empirical formulas, molecular formulas, and structural formulas. And these are all in the coming slides. So let's look at them. So our type of chemical formula. First, we have empirical formula. This gives the relative number of atoms of each element in a compound. It's the simplest whole number ratio representation of the type and number of elements present in a molecule. On the other hand, we also have molecular formulas. Those give the actual number of atoms of each element in a molecule of a compound. So for example, let's say we have the molecule C6H12. It has a greatest common factor of 6. That means the empirical formula for this molecule is CH2. There's 1 carbon for every 2 hydrogens. If I want the molecule that's exactly C6H12 though, I would give the molecular formula, C6H12, instead of the empirical formula, CH2. Well, in this example, they were different. They're not always different. So CCl4 only has a common factor of 1. So its empirical and molecular formulas are identical. Later in this chapter, we're going to talk some about why in the world the empirical formula exists. I think if you were to first hear this, you might say, well, why not just always use a molecular formula? It's more exact. Sometimes we can't find the molecular formula, and that has to do with how we make measurements. So sometimes we might only know an empirical formula. And for some type of compounds, a molecular formula is not going to make sense. And we'll talk about why when we get to ionic compounds. But there is a reason we're not just giving a name to something to annoy you, I promise. Now, a third type of formula, it has a different goal. It's a structural formula. This focuses on the shape of the molecule and the orientation of the molecule's atoms to each other. We'll focus on these types of formula in the next chapter. This chapter is primarily going to focus on the top 2. We'll get to the third one when we get to things like Lewis structures, where we're going to start worrying about what's the shape of our molecule. But until we start dealing with shape, we're not going to worry about the third type. I'm just going to say they exist here. So this will end our discussion on types of formulas. And next, what we're going to have to go into is how we can get some useful chemistry information from them in the concept of molar mass, which we'll do in my next video.